Welcome back. Section 4.3 subspaces. Definition. Let V be a vector space and W be a non-empty subset of V. Non-empty means there has to be something in W. Okay. If W is a vector space with respect to the operations on V, then W is called a subspace. You see, V is a vector space, W is inside V, it's a subset of V. If W is a vector space in its own right, using the two operations of V, then W is called a subspace of V. Theorem. Let V be a vector space with operations O plus and O dot and W be a non-empty subset of V, exactly as before. Then W is a subspace of V, that is, W is a vector space in its own right if and only if the following conditions hold. If U and V are any vectors in W, then U O plus V is in W. That is, W is closed under O plus. And if C is any real number and V is any vector from W, then C O dot V is back in W. That is, W is closed under O plus. That's it. So to be a vector space in its own right, if you remember, there are 10 requirements. 2 closure requirements, that is these two, and then 4 additional requirements of O plus and 4 additional requirements of O dot. Turns out, if you already have a vector space and W is a subset of that vector space, then W becomes a vector space in its own right. That is, W is a subspace of V if and only if just the 2 closure requirements are followed, are satisfied. Okay. So let's see the proof. Notice if and only if is a stronger requirement. Okay. It has to hold true in both directions. What does that mean? Onward direction. Suppose W is a subspace of V. That is, W is a vector space in its own right. Then W is a vector space under O plus O dot. And by the definition of vector space, W is closed under O plus and O dot. So that's a given because it's a vector space in its own right. Now the reverse direction. Suppose W is a non-empty subset of V and closed under O plus and O dot. We know that W is non-empty. So we want to show closure under O plus. Now this is an assumption. So what is there to show? It is closed under O plus. So that's first condition. Closure of W under O dot. This is also an assumption. You see, you know that it is already closed under O plus and O dot. Is the remaining 8 condition we want to prove. What are the remaining 8 conditions? First, O plus must be commutative. Well, O plus is indeed commutative because it was commutative in V, which is a bigger set. If a condition holds for a bigger set, then it automatically holds for a smaller set. What about associativity of O plus? Well, again, O plus is associative on the bigger vector space. So it automatically holds true for a smaller set. What about existence of additive identity? Now this is tricky because you know there is a 0 vector in V, which is the bigger set. How do you know it is in W? Well, we don't. What do we know? We know that W is non-empty. So there is some vector in W called, let's call it W, little w. Then 0 number from the real number line, 0 O dot W has to be in W. Why? Because W is closed under scalar multiplication. But 0 O dot any vector is the 0 vector. This is something we proved in our previous section. 0 O dot any vector is the 0 vector. Therefore, 0 vector has to be in W. That is, the additive identity of V lives in W. Okay. What about existence of additive inverse for every vector W in W? Let W be any vector. You know that negative W lives in the bigger set V. You know it lives there. How can we guarantee it lives in the smaller set? Well, negative 1 O dot W has to be in W. Why? Because W is closed under O dot. Okay, so the closure is so powerful that for any vector in W, its additive inverse also ends up landing in W. So, what about distribution of O dot over O plus? So, notice we finished all the four addition properties. Now, let's go to scalar multiplication properties. Is scalar multiplication distributive over O plus in W? Well, of course it is, because W is smaller than V, and this distribution holds for V. V is a vector space, so it's true. Is O dot distributive over real number addition in W? Of course, because again, this holds for the bigger set V. Therefore, it will hold for the smaller set W. Is O dot associative in W? Again, yes, because it holds for the bigger set V. Lastly, property of multiplicative identity for 1, the real number 1, and any vector W, 1 O dot W has to be W because that happens in V. W is in, little w is in capital W, which is sitting inside bigger V. So this holds in V, so it has to hold in W. All right. That is W O plus O dot satisfied all the conditions of being a vector space, so it is a vector space in its own right. All that we needed was closure. Closure under addition, vector addition, and closure under scalar multiplication, and of course W has to be non-empty. Let's start with examples of subspaces. First example, let's take any vector space. You know it has the A0 vector. Consider the set of only that 0 vector. Call it W. All right, this is a non-empty set. Moreover, 0 vector O plus 0 vector. Well, 0 vector, meaning of 0 vector is it adds to any other vector and gives you that other vector. Well, that other vector is itself. So, okay. W is closed under scalar vector addition. So, what else? Take any real number C. Scalar multiplication by C to the 0 vector is the 0 vector back in W. So W is closed under scalar multiplication. Therefore, W is a subspace of V. That is, it is a vector space in its own right. It is non-empty and it is closed under O plus and O dot. Here is another example. Let V be the set of all matrices, 2 by 2 matrices with real entries. You know that V, O plus O dot is a real vector space. O plus being the standard addition of vector of matrices, O dot being the standard scalar multiplication. Okay. Now, consider the set of all those 2 by 2 matrices where everybody is 0x, they are all real numbers, except we require that the top left be 0. So that A is required to be 0. Okay, so that A is not needed. All you have is 0 over there. Now W is a subset of V. W is non-empty because all I want is 0 here. I could put everybody 0. Such a matrix has to be in W. What is the requirement criterion to be in W? That the top left entry be 0. Well, this matrix's top left entry is 0, so it belongs to W. So you know W is non-empty. Now suppose you take 2 matrices from W, correct? 2 matrices from W, that is the top left entries are 0. When I add those 2 matrices, I continue to get top left entry to be 0. Okay? So W is closed under vector addition. Vector addition being simply matrix addition. Now suppose you take any real number R and a matrix in W, that is the top left entry being 0. Scalar multiple continues to give you top left entry to be 0. That is, W is closed under O dot and therefore it is a subspace of V. So here you have a concrete subspace of V. Now consider again the same example from before. V being 2 by 2 matrices with real entries and W be now the set of all those matrices, 2 by 2 matrices where the top left corner is 1. Let's check whether it is a vector subspace of V. W is a subset of V, W non-empty because placing a 1 there and zeros everywhere still is an element of W, so W is non-empty. Suppose you take two matrices with top left to be 1. If you add them up, notice how the top left has become 2. It is not in W, which means what? W is not closed under O plus. Well, it fails the closure requirement for vector addition. I don't have to check anymore. It's already not a subspace. Suppose here is another example. Suppose I take a homogeneous linear system. A is an m by n matrix. X is a column. Ax equals 0. So this is a homogeneous linear system. Let W be all those vectors, column vectors x in Rn, where x is a solution of this. That is, you are taking all the solutions of this linear system. Well, is it a subspace? Well, you know W is non-empty. That's the first check you have to see. Why is it non-empty? Because a 0 column will always satisfy this. Any matrix times the 0 column is the 0 column. So, the 0 column vector is in W, which means somebody is in W. W is not empty. Suppose you have x1 and x2, two vectors in W. That is, if they are in W, what does it mean? They solve this particular system. Ax1 is 0 vector, Ax2 is 0 vector. So you have two solutions. Now A times x1 plus x2. So notice I'm adding columns, multiplying by the matrix later. But this is something you saw in chapter 2. Matrix multiplication distributes over addition of matrices. So that is Ax1 plus Ax2. Ax1 is 0, Ax2 is 0, 0 column plus 0 column is 0 column. That is, x1 plus x2 also solves the same linear system. Therefore, x1 plus x2 is in W. That is, W is closed under vector addition. Suppose R is any real number and x vector is in W. X vector is in W means what? It solves the system. Now what about Rx? Rx, A times Rx. R is a real number. So real number, think of it. When you multiply by a real number, it multiplies every entry. So when matrix A multiplies to that real number gets multiplied to every entry of Ax. Ax is 0. So R times 0 vector is 0. In other words, Rx is also a solution. So Rx is in W. So W is closed under scalar multiplication, which means W is a subspace. All right, let's continue in our next video.